Good afternoon. I'm Dick Karp, the director of the Simons Institute for the Theory of Computing, and it's my pleasure to welcome you to the second of four open lectures this semester sponsored by the Simons Institute. Before I introduce today's speaker, Gary Miller, I should mention something about the future open lectures. On November 4th, the lecture will be given by Giorgio Ottaviano from the University of Florence, who's associated with the Simons program on algorithms and complexity and algebraic geometry. And on December 8th, the speaker will be James Lee, a Berkeley PhD now at the University of Washington. And his talk, like today's, will be associated with spectral graph theory. So Gary is a Berkeley product. He got his PhD from Berkeley in 1975. His degree is actually in mathematics, and his advisor was Manuel Blum in computer science. And Gary is actually an ideal role model for the kinds of people we want to be producing in the future at the intersection of theoretical computer science and mathematics. Gary has worked mostly on computational problems in a number of areas of mathematics. He gained fame very early for his PhD thesis on Riemann's hypothesis and tested primality, where he gave a polynomial time primality under the assumption that a certain version of the Riemann hypothesis is true. And the algorithm that underlay that one was also the basis for the later Miller-Rabin randomized algorithm, polynomial time algorithm for primality testing. Gary's worked in computational geometry, computational group theory, number theory, graph theory, linear algebra. A great deal of his work has been associated with mesh generation and numerical analysis. He's a recipient of the Knuth Prize and the Kanellakis Prize. I remember a few years ago visiting Carnegie Mellon, and Gary told me that the great advances that were to come in combinatorial algorithms, network algorithms, and the like would derive from linear algebra. And that totally went against my intuition, because I always felt that flow problems should be solved by pushing flow one path at a time. But I was completely wrong, and I'm very happy to acknowledge that. And Gary's going to tell you about some of the ideas that have led to a true revolution in that area of computation.
Thank you, Rick. Thank you very much for the very kind introduction. It's a pleasure to be back here. I guess it's been many years. 75 is a long time ago. Anyway, so but today what I'd like to talk about is what I see as a revolution in graph theoretic optimization. So this is joint work with a lot of co-authors: Guy Bloch, Wei-Hung Chen, Michael Cohen, Anupam Gupta, Jonathan Kellner, Jonas Kudis, Alexandra Madre, Jakob Pakach, Richard Pang, Kanat, and Shen Xu. So anyway, so there's a whole bunch of people involved in all this work, let alone all the other work that I'll reference in the talk. So overview of the talk will be, we'll talk about linear system solvers, and I'll use a simple example in regression and image denoising. We'll start with a simple formulation, which will give us the class of systems we'd like to solve. Then I'll overview what are called solvers for what are called symmetric diagonally dominant systems. And then we'll do a better formulation with L1 and how this is related to max flow. And then a whole bunch of new work that's come out in the last year or so. It's very exciting. Okay, so what is spectral graph theory? What we want to do is use graph algorithms to solve linear systems, and use linear algebra to help solve graph problems, and both of them together to solve optimization. So the idea is to mix both graph algorithms, which will be fundamental, as well as linear algebra to solve problems in this general area of optimization, where somehow under the hood there's a graph running around. Okay. So probably the oldest of all computational problems that goes way back is given a linear system, of constraints. And what you'd like to do is then solve this linear system, in this case for x, y, and z. I'm not sure I know this answer. Maybe you could work this out if you get bored. And to figure out to find the solution to this problem. So this goes way back. So actually the first known records of this, probably goes much earlier, is to way about the 1st century AD. There was work by the Chinese on how to solve such linear systems. I think actually they were solving a stronger problem, an optimization problem of distributing corn or something in China. But anyway, it goes way back. So of course, somehow it's called Gaussian elimination. And as I understand the story is that they were writing a textbook, and Gauss got assigned the chapter on solving linear systems, and so they gave his name to it. But anyway, it goes way back. So of course, the big breakthrough was then in '69 when Strassen showed that, in fact, you could do it faster than n cubed. This is a major breakthrough. Over the years, Smith, and Winograd improved this to n to the 2.37. And then this got improved. Eventually, Vescott-Williams showed that this can be done, and the state of the art is 2.3727, right? So it looks like, as far as I can tell, that the answer probably is that it's n squared, but who knows when we'll finally figure that out. So there was a lot of work on using graph theory to solve linear systems. And most of these methods were trying to sort of speed up Gaussian elimination in special cases. Alan George worked on this in the 70s, Lipton Rose Tarjan in the 80s. And more recently, there was some nice work of Alon and Oster who showed that you could use sort of nested dissection-like algorithms for even the directed case. This is very nice, but we won't talk about this here. So let's go to a simple example where you get linear systems. So you have a bunch of data, and what you'd like to do is fit a curve to that. So the simplest in this case here is a straight line to some data. How should we do this? Well, we could set up a linear system where A then is a linear system. We're trying to find 2 variables in our case. X is actually just 2 variables. In general, it could be more. But unfortunately, the problem is over-constrained, right? There's no way we're going to be able to fit a curve through all those points that you saw. So what do you do? So if you look at Strang, he says, well, you simply multiply both sides by the transpose of the matrix. And now the system is solvable. And not only that, the system has a nice property that it's symmetric positive semi-definite. Or in general, just say symmetric positive definite. Okay. So the real big open question in this whole area is, can you solve any symmetric positive definite system, even if you're given it in the form A transpose A in subquadratic time? And chances are that will probably be solved, if I was going to guess, in the next 4 to 5 years, that we'll get better algorithms for that. People have already made a huge amount of headway. But for us today, what we're going to need is a matrix of this form for which they come from a graph. So that's what we're going to assume, right? So another higher-level idea here is that we're going to do approximation algorithms. So the first cut, we don't want to solve these problems exactly, but we just want good approximations. So in the NP world, where we don't believe there is a polynomial time algorithm for solving them, there's whole conferences about approximating NP hard problems. So what I'd like to do is use the same kind of ideas, but instead let's use this for everyday mundane polynomial time problems. Okay, so we want to solve those quickly, but we only want to do them approximately to start with. Okay, and we want to do it much faster, right, than we know how to do them for the exact solution. So in particular, we'd like to really get it down to linear in the input size. And it may be that we get for free then even faster algorithms for exact solutions, but let's leave that for another day, right? So that's what we'd like to do. So what I want to do is go through a simple example where we do a regression problem. This is for image denoising. So this is a critical step in image segmentation and detection. And a matter of fact, if you do denoising, I think it actually makes a segmentation problem almost obvious. So it's not really clear that we're doing image denoising. We're probably doing something much stronger, but let's leave that. So a matter of fact, so this is an example. So one of my former students worked on questions like, how do you, this gentleman here is sitting behind a special camouflage material that takes on images from the background, and what he'd like to do is segment that out. And using simple denoising algorithms we'll talk about, he's able to segment out this TARP. Sort of a simple example, but anyway. So what's the image denoising problem? So the assumption is that we have an original noiseless image. Noise is generated from some distribution. And what we're given then is the original image plus noise, and our goal is to approximate the original image. Okay? So let's use letters. So we'll say that S is our input, the original image plus noise. X is what we're trying to find, and then the noise would be S minus X. Okay? Good. So how do we set this up as an optimization problem? What we'll do then is we'll say that the noise is small, so we should be, that the X we return should be very close to the original image. This is some kind of fidelity term. It also should be the case that the image is smooth, so there should be some function computed on the difference of neighboring pixels, some way of saying the image is smooth, okay? A smoothness term. And so what we then would do is, as an optimization, in this example here is, suppose we have this noisy image, so we could say that a candidate thing to fit this would be this stepwise function, okay? So in particular, this should minimize some kind of fidelity term plus a smoothness. And let's just pick something simple to start with. Suppose we say that we minimize the sum of the differences between the neighboring pixels and the, let's see if this works actually. So between between the value we return and the value we see, this should be small, so the sum of the squares. Should also be that we want some kind of smoothness. The most naive thing to do is put in here this term, which is the drop between neighboring pixels should be, the sum of the squares should be small. This actually is a toy example, and we'll see that later on there's better things to do. But anyway, let's just do that. But when you work it all out and you say, well, that's an optimization problem, and magically it corresponds to solving a linear system, that linear system, it has a very nice form. What it has is that it's, first of all, it's both symmetric, here when you work that out, and it also has a nice property that the sum of the absolute value of the off diagonals is less than or equal to the diagonal. So in this case here, it actually is equal, right? So these kind of matrices here are what are called symmetric diagonally dominant systems. And you can also think of those as a graph. When we have a non-zero entry off the diagonal, we'll think of that as an edge between two nodes here, right? So this is an edge between, say, vertex 4 and vertex 1. Okay, so we get some kind of graph. Good. Matter of fact, the reason is because when you set it up, it is the thing we started with was a graph, but let's just go on. Okay. So what's interesting is that many algorithm problems in computer science can be couched with an underlying graph, can be couched as an optimization problem. So the simplest would be the max flow, shortest path, maximum matching, scheduling, and MINCUT. I claim these all can be couched as some kind of optimization problem. And they have a natural underlying graph because they come from graphs. Others is not so clear, like the longest common subsequence. But these problems here all have this nice property that there's an underlying graph, and we could couch it. So you could say, well, great. What we could do then is say, well, all those can be written, I claim without not too much work, as simply a linear program, right? A linear program then is, instead of having equality constraints, we have inequality constraints, and we have a direction we want to head, and we're just trying to find the point furthest in some direction. Okay? So the simplest of all these to do, and I think we do this in CMU undergraduate class, is we say, after we've described linear program, we ask the students to write out when we've done the single source shortest path, we say write out the linear program for that. At a first cut, this seems like a terrible thing to do, right? I could have couched this problem as, for instance, the halting problem also, right? And it wouldn't have, so it's not clear at all what I've done useful in this case. But as we'll see, actually it's not that unusual. That in fact, it may be that at least in the parallel regime, the single source shortest path, the only approach to doing that may be through linear algebra, through LP, and not actually as a discrete combinatorial construction. Okay. So let's just go through Laplacians, because remember, Laplacians are somehow important in all this. So you just saw a Laplacian, but let's understand them from sort of as a primer here. So what I want to do is find a matrix which takes you from flows to residual flows. So this is going to allow us to couch problems like the max flow problem, where for most vertices we want the flow in to equal the flow out. So here's a little graph. I've arbitrarily oriented the edges, but you should think of those as undirected, but they're oriented. And what I want to do is lay out a matrix that looks like the following. I have two edges, so I'll make two columns. I have three vertices, so I'll make three rows. And what I'll do here is I'll put, for this edge here, I'll put a +1 at the head, and a -1 at the tail, and 0 otherwise. And I'll do the same for this. And then I claim that if you think of this as a flow on the edges, so I have a flow of 2 that goes from 1 to 2, and a flow of -3 on this edge, which means it goes from here to here, when I multiply this, I claim you get the residual flows, the flow that must be exiting and entering those vertices. Let's just go through that. So this gives us a very nice way in linear algebra to code up things. So let me just say it one more time. So given a graph, we'll make up a matrix B. It's going to be a vertex by edge matrix. There'll be a +1 if VI is the head of edge EJ, -1 if it's the tail, and 0 otherwise. Okay? So what this does is give us the flow. So let's just see it one more time. So in the example we had before, what we had here is we have our vertices. There was a flow of 2 in this direction, 3 in this direction. So this vertex is going to lose 2 units of flow. This vertex is going to lose 3 units of flow, and this vertex is going to gain 5 units. So that's what this codes. So the beauty now is from now on, all we have to do is claim we're doing matrix vector product to figure out residuals, or to couch things like the max flow problem. Okay? So let's do one more thing, and that's let's look at B transpose, right? So now we've transposed the matrix, so now it's an edge by vertex matrix. So if we let V be a column vector of potentials, then when we multiply this, I claim this is going to give us a vector of potential drops across the edges, because remember, this is going to be a column vector of size the number of edges. Good? So if, on the other hand, now we add some physics to this, we decide for a given potential drop across the edges, let's make that into a flow by, say, having resistors. Say, let's let R be a diagonal matrix of unit resistors. Then by Ohm's law, this ends up being a flow. Okay? So just to simplify this today, let's assume that all our resistors are 1. So this is just the identity matrix, and I'll throw it away. So the bottom line is this matrix here is nothing but a vector of flows. So what happens then at a high level is we have a matrix that allows us to go from potentials to flows, and the original matrix allowed us to go from flows to residual at the nodes. So why is this all important? Because then we can define the graph Laplacian. So the graph Laplacian now is just this matrix here. It's B times B transpose, okay, of some graph G. So the goal then for a lot of this lecture is to be able to solve this, or at least approximately solve this system. So let's just step back and look at what we're supposed to be doing. So if we write this out, expand this back out, we have this matrix. So notice we said that when you multiply this potential times B, you get a flow. So, and on the other hand, if we took that flow and we multiplied by B, which is what this term would be, we would get our residuals. So notice that what we've done is we're finding a flow which matches some set of demands at the vertices. Okay, so the next question you could ask is, what can we say about this flow? And I claim that this is a very special flow that we get out of this. This is what's called a potential flow. So let's step back. So you can imagine having two kinds of flows. You can have flows for which there's circulation. All they do is they're just flows that run around in the graph, but there's no residuals, right? So the flow into every vertex is 0. The flow in is equal to the flow out. Good. On the other hand, you could have flows, which we'll call potential flows, which are derived from some potential. Okay? So the first simple claim is that these two flows are actually orthogonal. In other words, if you view these as two column vectors and you dot them, they're orthogonal. And the proof's trivial. You simply say, let's look at the dot product. Well, this is a potential flow, so we can just replace this with some potential. Then we can rearrange the parentheses into a transpose. But this now is a circulation, so it's 0. So 0 times V is 0. So what we've just proved is that all the flows can be decomposed into there's two kinds of flows, and they're orthogonal to each other. Okay, this is sort of a very old fact, but so let's just finish this off. So notice the potential flows. Well, every time we set the voltage, we may get a different flow, and if the graph is connected, actually, it's not too hard to see that they always give you something new, except for when all the potentials are equal. So you get a subspace of dimension n minus 1. On the other hand, if you look at the circulations, they end up being of dimension m minus n plus 1, where remember m is the number of edges, and n is the number of vertices. So what's this? This is just the number of non-tree edges you get from any graph. Because I claim that if you take any spanning tree of your graph and you look at the cycle you get that induces that non-tree edge, that each of those gives you a circulation around there. So if you didn't follow this, it's not too crucial. But what it says is that we found a decomposition of the flow space into two orthogonal subspaces. So it means that whenever you have a flow, you can always think of it as being two parts. It's both has some circulation part and it has a potential part. Okay? So the other simple fact, maybe we shouldn't worry about this here, is that we get another property, and let's leave that, and that is it's the case that if it's the case that that if we solve the following problem, we get a potential flow. So suppose we look at all flows that meet some demand. They have the same residuals. But over all those, we take one of minimum energy. I claim it's not too hard to see that by orthogonality, it must be the case that this flow is just a potential flow. Well, let me not go through the proof here. I realize that but it's very straightforward, and it's a nice, simple fact. So it says that, in fact, there's two fundamental ways to solve graph Laplacians, right? One of those ways is, so the two ways, and they're dual of each other, of solving this problem, and there's algorithms now that do this and combine them both. One is the classic way. You say, I'm trying to find a V so that this is small, so I minimize this error. The other is, what I do is I find a flow that meets my demand, and I just start changing it by circulations until I minimize the energy. And so these are sort of the two fundamental ways that we know of for solving this, and then more generally of combining these two. Okay? Good. So let's just do this one more time. So what it says here is that if you take your favorite flow, it projects onto a potential flow, and it has a circulation part. So if what we do now is we say that if this line here is all the flows that satisfy our demand, right? We're trying to find this point. This is the solution to our problem. And we have so there's two ways to do this. One is we start with any old potential, and we start modifying it, trying to get closer and closer to one that meets our demands, right? So we keep moving our way down until we do this. And so an obvious thing to do would be to do some kind of gradient descent, minimizing this difference, okay? So that would be the other. The other is we start with a flow that meets our demand. It's not clear how you do that, but I claim it's actually quite easy in this case. And then what you do is you keep trying to remove circulations until it's a pure potential flow. Okay? And so then and the simplest of all is the algorithm is you pick a single cycle and you remove that circulation from your flow. And so those are the ways, what's known methods. Okay? So what happened is that I guess since the 90s we've been working on solving graph Laplacians, but the first really major breakthrough was this paper by SPIELMAN-TENG in 2004. I think it's something like I'm not sure how many papers it's decomposed into now, but it's like an 80-page paper for which if you have an afternoon you can read 2 or 3 pages of it. Roughly that's what I say. And as far as I can tell, every time someone comes up with someone new, they say, well, if you had gone back and read page 46, you would have seen some clever trick, or they read page 46 and now they're applying it. But it's an amazing paper. But anyway, so what they were is the first ones that gave a near linear time solver. And then some work with Kudis and Tang, we were combining with their work, we were able to show that in fact now you can solve these symmetric diagonal dominant systems where m is the number of non-zeros and b is some vector. you can solve it approximately, worry about the details, in m log n time. So it's something similar to like sorting, right? So the runtime is about the cost to sort, right? Constants are probably not that small, but okay. And then at some point later, we showed that you could parallelize this. And so why is this interesting is that this allows us to actually get a better parallel algorithm for single shortest path because of the LP stuff we talked about. I won't go into that. So you get a depth here, which is m to the 1/3, which wasn't clear. Okay, good. So what's interesting, though, is to look at the runtime of these algorithms over the years. So what's the constant C? So the original Spielman-Teng constant, according to them, I'm not sure I actually know that for sure, but it's 70. At some point, it got reduced to 32 by some nice work, and then to 15, and then to 6, and then to 2, and then to 1. And more recently, it's down to 1/2 of a log. So if you notice, we seem to get a speed up here by decreasing the constant C by a factor of roughly 2 to 3 every few years. So it's not clear what the curve should be, but it seems like it shouldn't be that long before we at least get rid of maybe this half log. I guess we're supposed to go to a quarter next, right? Because we want to keep publishing papers, and you wouldn't want to get there right away. So, right? And everyone has to, get jobs and all that. So anyway, so that's what's happening here. Okay, so there's other very nice work of Kellner, Rekio, Zidford, Zhu, and Lee and Zidford. So what they did is they showed that, in fact, if you do the other approach, which is what you do now, is you start with some flow that meets your demand and seek removing cycles from it, you can actually get an algorithm that is almost as good. They claim it's better, but of course I can't say that. So they get a runtime that looks like this. And it's not clear in practice which would be better, but they get an algorithm that runs very, very close in runtime, right? And so there's these two approaches. Good. So at a high level, so how do these potential solvers work? Well, one nice way to think of this is what you're doing is you're saying if I want to solve a symmetric positive definite system, if I write out this optimization problem here, then I claim that the solution to this is a solution to our system. And this is not too hard to see. What you simply do, assuming you're a facet with gradients, is you compute the gradient of this, and magically it comes out to this. You set it to 0, and then you see that you found a solution. Okay? So really, solving these systems is some kind of quadratic minimization. Okay? So in fact, what you would do then is something that looks like that. What you do then is you simply say, okay, I want to solve this system. You make an initial guess, say all the voltages are 0, and then you keep iterating this, doing some kind of gradient descent, right? This is some kind of residual error you have, and then you keep adding that in, right, or subtracting it off. Okay? The only trouble is it may converge very slowly. Even in 2 dimensions, this has problems, right? That what's not clear until you work it out is if you go skiing in an elliptical bowl and you always ski directly downhill until you get to the lowest point on that curve and then you ski again, you actually you end up having to make a lot of turns on the skiing. It's not clear at all. You would think that what would happen is when you skied down, you would get to this axis, you would stop, and then you would head downhill, but that's not what happens. Okay? So it's not so good. So what's the workaround? The workaround is what you do is you use preconditioned iterative methods. In other words, let's solve this system instead, where some matrix B. Notice that I didn't change the solution, but I did change the recurrence. So when you write this recurrence out now, it looks something like this, right? Because you have this B transpose here, so if I put this inside, it would be the same. This would have a B inverse here, and then you'd have a B inverse here. But notice the way to think of this now is that this gives a way. So what you would do is you would take your guess, you would compute the residual error in the old system, and then you would do a solve here. So what happens then is you would recursively then solve this linear system here, which is you would solve for Z in the system, and this would be what you would replace this with, the Z value. So what happens at every round is you solve a recurrence, and and hopefully you need it to be the case that, of course, the two properties you'd want it to be is, first of all, it should be easier to solve this system, and it should also improve the number of iterations you need to do. So that's the goal. And so this is a very classic.
Excuse me, you're going to need a plastic, otherwise this won't converge.
Here?
Yeah.
Yeah. So I think I had one and then I took it out at the last minute. I got nervous. Sorry. So this should be a plus, okay? I would draw it on the screen, but then they couldn't ever take it away. But, okay, sorry, thanks. So what was a big breakthrough? In 1991, Fai just said the following. I guess he did a huge amount of work on linear programming, and he was interested in these problems, and he said that if you're looking for a preconditioner for a matrix that comes from a graph theory problem, you should probably look for a preconditioner that's a graph. You should not look for something else. Okay? And so that was one observation. He said, of course, also people know that you should be using some kind of Chebyshev iteration. So he made these two remarks. And really, one way to think of it is that all the rest of the talk, if I had this and you have a bunch of smart people, all you have to do is take this and you can work out what's to come. But let me give the story anyway. Okay. So those are the two tricks. So what we're going to do is we want to precondition this. So what's the obvious thing to do? I want to have this big graph I want to solve the Laplacian for. So I need some other kind of graph which is somehow simpler. Okay? So this is actually a study that's been done in computer science for quite a while of how do you take a dense graph and throw away most of the edges so that it's somehow equivalent to the old graph. So this has been done, for instance, in spanners. So you'd like to preserve distances in the original graph, right? So you're trying to do, you have some graph of distances, and you'd like to throw out most of the edges, but still have the distances about the same. So you do spanners. Bender and Karger had this whole problem with cut sparsifiers. You'd like it to be the case that the cuts in the new graph are the same as the old. Well, observe that once you've done this, to make this true, you better weight the other edges heavier. The edges you keep better have heavier weight than before. Otherwise, this is, of course, impossible, right? If you throw edges out, then the cut must get smaller, so you have to make up that by increasing the edge weights. And what we're going to do here is we're going to use what are called spectral sparsifiers, for which it means that they're spectrally equivalent, whatever that is. But I don't think that's critical for this. Okay, good. So let's just see this in action. So here's a complete graph. And what I'd like to do now is pick n log m samples uniformly, and I get a new graph. So what did I do? I ran, I think Richard did this, but he ran some code, and it picked randomly some of these edges. It kept those edges, but it made them heavy, so that now I claim that these two graphs are spectrally equivalent. Okay? So that's the trick. The idea then is that we'll just sample edges and keep those edges, but keep them with a heavier weight. Okay? Okay. So now the question arises, if the graph is not uniform, I probably shouldn't be allowed to pick edges with the same probability. I have to vary that probability. And what is that magic number? Well, Spielman and Srivastava had the answer. They said what you should do is you should take every edge of your graph, you should take a multimeter, and you should put it down at the two ends of the vertex, u and v, and you should measure the effective resistance in that graph, right? How much it looks like using the whole graph. And that should be your sampling probability. And then, of course, if you keep the edge, you should, in fact, keep it with weight 1 over that probability. Okay? And you should do this log n times. And the reason for this is because you need some kind of matrix Chernoff bound. That's the way to think of that these days. But you have to oversample so you get some kind of concentration. But this is a very beautiful, very influential paper on the whole area of sampling in graphs. Okay. And then there is another very cute observation that maybe you can work out, and that is if you take the effective resistives in your graph, say unit weight resistors, and you add them all together, magically you get n minus 1. I think this is known as Foster's theorem. But it's a cute exercise to convince yourself of that. Okay? Okay. So we can get down to n log n edges easy using this. There is a slight problem, though. How do you calculate these sampling probabilities? Well, Spielman and Srivastava said it's no problem. You just use a Laplacian solver to do that. And of course, and then Spielman and Teng wanted to, in their algorithm, and all the others, they needed these for their sparsifier. So we end up with this chicken and egg problem, right? So what we'd like to do is sample the edges with effective resistance, but in order to do that, we have to do a solver, and so we're into this vicious cycle. So how do we get around that? What we'll do then is you can reprove their sampling theorem as long as you have an upper bound on the effective resistance. You may get more edges, but it still works. Okay? So that's going to be the trick. Good. So how do we get an upper bound on effective resistance? What we'll do is, did I skip a slide there? No. Okay. So, so what we'll do is we'll compute this in what's called a low stretch spanning tree. Okay. So one thing that happened. See, over the years I teach these algorithms classes, and we always have to do min-weight spanning trees, and I do that lecture, and then I sort of imply that spanning trees are done, right? What more would you want besides a min-weight? Now my feeling is just the other way around. I believe that our grandchildren will still be messing around finding better spanning trees and better algorithms for them than we have. That I think that that will never be done with spanning trees. But let me just give you sort of a point here, and that's, let's look at what are called the stretch in a tree, okay? So here's, my underlying graph now is just a square grid, and I've picked called a hair comb spanning tree for you. And what I want to do is look at the stretch of edges. So the stretch of an edge is defined to be the distance in the tree versus the distance the edge itself. So this edge is, say, all edges are 1. So this is 1. This is 3. So the stretch for this edge is 3. Good? On the other hand, if we take edges on the farther side of the spanning of this tree, if this is square root of n by square root of n grid, these edges are going to have stretch about square root of n. So as a matter of fact, almost all the edges here, half of the edges are going to have stretch about square root of n. So unfortunately, we get total stretch, which is n to the 3 halves, okay, which is too much. So there's another one construction, which is the recursive C, which I claim does much better. So let's look at this tree. So this is a construction for which what you do is you recursively make spanning trees for each of the 4 quadrants, and then you hook it together with a little c. Okay? Good. So now notice that we didn't change the worst case stretch. Matter of fact, it's worse now. This edge here is going to have stretch by the time it works its way all the way around to the other side, may have stretch more than it had in the comb, but that's okay. On the other hand, there's a smaller number of those that have that stretch, okay? There's only square root of n of those. And there's only log n levels, so we get n log n total stretch. So this is an example where this tree then, from the point of view of stretch, is much better than the comb construction. Okay, good. Okay, so we're able to do that for any graph. So a matter of fact, this first was used in a paper here from Berkeley on the Lone Carpelic West, where they used this, I believe it, for the k-server problem. But they defined the notion of a low stretch spanning tree, and they were able to get stretch, which is about m to the 1 plus epsilon. Okay, very quickly. Good. And then there were several improvements of that, getting it down to stretch, which was m log squared n. And this can be found again in now almost the same amount of time, n log n time. Okay? And then with a few more work, finally in some work of Abraham Neyman, get it down to the total stretch is, ignoring log-log terms, is m log n, and a runtime about m log n. Okay? So now these spanning trees you can find very quickly, and they all have small stretch. Good. So let me explain how the solver works at a high level, just with go through it. So I want to solve the Laplacian on this graph. So the first thing I do is I find a low stretch spanning tree. Then the next trick is we'll take all those edges, we'll make them heavy. So I made those heavy. So notice that my preconditioner for the original graph now is this graph with these heavyweight edges. So I have to pay for that. And that's the first level of spanning tree. For the next one, what we do now is sample the off-tree edges. And we get this graph. Then what we do is now apply Gaussian elimination to remove degree 1 and 2 vertices. So we do that. And then we recurse. So that's, I think, all you want to know about that algorithm. Anyway, so that's the algorithm up to m log n. Okay? So there's been all kinds of nice applications of this. Probably the first application of Laplacians was Tutch showed how to use this to draw a graph. He said that what you should do is nail down the outside face, replace all the internal edges with springs, and just let it come to an equilibrium. And assuming the graph is 3 connected, you get a nice layout. Okay? There was another nice paper by Bowman and Henderson, and what they did is they showed that if you're doing finite element simulations, the heat equation, well, notice that we've been just thinking of electricity as flowing along the edges. So we've only have flow in a one-dimensional world. But if you're doing like a heat on a plate, then the flow can flow in 2 or 3 or many dimensions. So you need to have some way of being able to claim that you can solve those problems by only having the flow on the edges. And they were able to show that by showing that flow on the edges gives you a good preconditioner. So then there was some work on learning. So there's several papers using this to do learning theory. So there's this very beautiful paper by Kellner and Madre who show how to generate random spanning trees in n to the 1/2 time by speeding up random walks. So the idea is that if you do a random walk, you can get a random spanning tree, but unfortunately that could be too slow, and so they were able to speed it up by using graph Laplacians to speed up the walk. So one of the most beautiful papers in this whole area, you know, whether it's that hard is not that crucial, but what they did is Dash and Spielman showed in 2008 that if you take directed max flow, min cost max flow, lossy flow, all can be solved using linear programming interior point methods where the pivots are simply symmetric diagonally dominant systems. So the way to think of this at a high level, I think you get slightly better bounds, but it says that if you're doing interior point, you're going to use about m to the 1/2 iterations. Each iteration is a Laplacian solve, so you get an m to the 3/2 runtime. So this is very interesting in that it says that all these kinds of problems can be done with interior point type methods, right? And of course, since no one believes that interior point really needs m to the 1/2 time, it's not clear whether this is just a linear time algorithm in its own right. But that's to be seen. Okay. So one thing to do is go back to the smoothing problem for images, and what we did is our smoothing term was this quadratic minimization, and unfortunately that's not so good. What it does is blurs the smoothness we picked, blurs out edges, and they remove boundaries. They don't like jumps in the data. Where notice really what we'd like for image processing is suppose that in fact if we use an L1 smoothing, in other words the sum of the absolute drops, then this gives us a better, it doesn't mind fast drops because it says that putting all the drops at one place is just as good as spreading it out, right? So notice here that both of these from the L1 point of view have the same objective, right? This is just as good as spreading the drops out as having them all in one place. So it does much better for fitting. Good? So in fact, what we do is replace this with an L1, and this gives us a nice property that as you vary the weight between these two objective functions, you get images that go from very noisy to caricature. And so this is well known. But you should, let me just point out that this problem also is really related to a very classic ST cut problem, and that is I've given a graph, and I'd like to cut the minimum number of edges that separates S from T. It's not too hard to see that the min ST cut is the same thing you get by minimizing the sum of the drops over all the edges, subject to the condition that you set the value here to be 0 and the value here to be 1. Okay. So this gives a min cut. Can't prove it here, but so this problem then occurs as a very natural graph theory problem also. So then there was a very nice work by Cristiano and all where they showed that in fact you could use multiplicative weights to do the undirected max flow and min cut problem. And again, what happened there is that you used about m to the 1/3 solves of a symmetric diagonally dominant system. So this gives you then a method for solving these kinds of problems that's faster than was known at the time, right? So this gives you m to the 4/3 runtime. So actually we played with this. So Stan Osher said that he was interested in some other version of this, which is where you'd like to have a rotation invariant version of this, and that is it should be the case that as you rotate the pixels, the objective function should not change. So he said he'd really like to have the drops to use some kind of, instead of using the sum of the drops in the x and y directions, we should use the L2 drops instead. And when you work that out, you can, and use this smoothness. And this works actually pretty well. I'm not sure, I guess. So what happens now is you can view this problem really as what you're trying to do is minimize the drop across a block of edges where now you take an L2 drop across them as opposed to L2 squared or just the L1. Okay? So notice that this is really just a slight generalization of what you've already seen. So anyway, so we were able to show that you could do that for this problem. Maybe I'll just go on to. So in the next few minutes, unfortunately, let's quickly go over what's happened in the last year or so, because there's major things have happened. Okay, so probably one of the major things that happened, at least, is a paper out of Berkeley here by Lee, Rao, and Srivastava, who showed the following, that in fact, if you're doing the max flow problem, you could view it as some kind of generalized descent for a class of Lipschitz convex functions. But now what you do is instead of doing our gradient descent as we have it, use another method called Neserov's optimization, and replacing some of the L infinity with a soft L infinity and a smooth version of L1. And magically, you could re-get the result of Cristiano and all using this kind of thing together. But this paper caused all kinds of interesting work to be done. So in particular, Sherman here, a graduate student, showed that in fact, you could now do approximate max flow in the undirected case, or MINCUT, in almost linear time, m to the 1 plus delta. Okay? And this uses some earlier work of Madre on fast approximate MINCUT algorithm. So that was a major breakthrough. And then at MIT, they also had a paper by Lee, Kellner, Lee, Arecchio, and Zidford, who showed that in fact you can get this, you can actually do the max flow, and they use a different approach, and they precondition with Reikki's approximate oblivious routing ideas. I can't go into that here, but so that's very nice. So there's a huge breakthrough in this on these problems. And then based on putting the two solvers together and some work by Cohen through Rao, they were able to show that in fact, if you have access to a low stretch spanning tree, you could actually speed up the algorithm by removing half a log. Okay? And this is interesting for two reasons. So one is that there was two places in the KMP algorithm where you picked up a log. One is because it seemed to require matrix Chernoff bounds, so you had to oversample by a log n factor, and there was also the runtime in the low stretch spanning tree. Okay? So let's see, do I want to talk about this? Why don't I just, so the basic idea that gets around this is what we did is cheat. What we did is instead we allowed Steiner nodes, and we also decreased the cost of high stretch edges. So we said that instead of the stretch of an edge being the old stretch, what we did is we took it to the pth power. So the effect of this is to say that for very large stretch edges, they won't cost us as much anymore. And this doesn't seem to affect the runtime of the algorithm. So this was good enough. Okay? So another way to say this is that if you look at the old AKPW low stretch spanning tree algorithm, it had a great runtime, and it had too much stretch, even in this p-norm stretch, where if you take Abraham Neyman, they have the property that they have runtime with a log in it, but they get very good stretch. So the effect was to put the two together, and you get the best of both worlds. Okay. One more thing, and then I'll quit. And that is, since then, Spielman and Teng have actually come up with a parallel algorithm for Laplacian solvers. And that has a nice property that, so what they're able to do is take a symmetric diagonally dominant system, and they're able to write it as a product of k-sparse matrices. Okay. And so they were able to get a sparse representation for the inverse of the matrix. Notice we didn't do that in the other algorithm. All the old algorithms just were straight solvers. So what's nice about this is they get now an algorithm that has a runtime which is polylog m with some polylog terms here, and the work is still near linear. Okay. So why is this interesting is that it could be the case that in the 80s and 90s, we had all kinds of problems finding fast parallel algorithms for graph problems. Single source, shortest path, all those kind of problems seemed to give us a lot of trouble. We didn't know how to get algorithms that were competitive with standard sequential algorithms no matter work. And this probably will make it possible then for all those problems now to be solved very fast. Whether it's practical, that's another question, but at least theoretically it allows us to go back and rethink all the old parallel algorithm stuff. So of course, you know, what are some future work? Well, it'd be nice actually to see some real implementation. John Kudus has some code from older work, and that's very popular. But it'd be nice to see some of this stuff coded up and have it affect everyday world. So it'd be nice to get near linear time algorithm for exact max flow. And it would be nice also for these algorithms to have dependency. The flow algorithms are not as good as the solvers. They don't have a log 1 and epsilon dependency. Their dependency is just 1 over epsilon, so that's an open question. And of course, another big question is, can you get subquadratic symmetric powers and definite solvers? Okay, and I think I'll leave it at that.
That's a fantastic set of ideas. So if anybody's looking for a thesis topic, it's predictable that there are going to be about 10 more breakthroughs in the coming year. Questions?
I have a couple of questions. One, I'm not sure what the concept of approximate minimum cut is, because a cut is a partition. So it's either you're on one side or the other. I'm not sure what it means. And before you answer me, I have a second question, which is what you propose about the square root function in the fidelity or the
Okay.
signal term. This makes it a minimization of a concave function, which in general is hard. So I'm wondering how this approach works in this case.
So let's see. So the MINCUT, that's a good question. Maybe someone else knows better than me. But I think what you end up doing is
It's probably getting
yes.
attention.
So it at least works in the following sense. So when we're doing the L1 minimization, we get that. Yeah. So then the question is, how do you convert the L1 minimization into a cut, right? In the limit, you get a cut. And the question is, how do you do that after doing this, right? So that's a nice question.
You can random threshold the function to get the
Yeah, you just take the potentials you get. You go from the flow to a potentials, and then you do say a threshold cut over those, right? I think that that's
Yeah, you could do some kind of rounding.
you're right. And then I think that that's only going to give you an approximate cut then, right?
And the approximation is also epsilon?
Yeah, I think it's not good. I'm not sure how many exact epsilons for that. It's a good question.
And about the second question?
So the other one actually, the idea is we do some kind of multiplicative weight where you take a whole group of edges at a time and you reweight them simultaneously. I could go through the algorithm for you. Ran out of time. Sorry.
Question back there?
So another popular source of linear time solvers is multigrid. Does that play a role in this community?
Yeah, so there's a lot of overlap with this. I mean, at this point, so we diverge as a community, right, looking at problems. And it looks like that there's still a lot of overlap, but it's not exactly clear. I mean, one slight distinction between the multigrid is usually these come from, say, finite element, say for the heat equation, for simplicity. And in that case, you assume that all the edge weights are almost identical. So here, the edge weights vary by huge amounts, especially by the time you do multiplicative weights. They may vary by, you know, some huge quantity, 10 to some huge number, right? So the edge weights then go crazy, in these, and they still work. This doesn't really care. But on the other hand, you know, clearly it was motivated by those ideas, right? But something slightly different about this idea of your low stretch spanning tree and stuff, right? I don't exactly understand.
Is there a further question?
That's right.
So Gary can